if we set up such an experiment where we have a light source like a lamp and two very narrow slits, we would, if the conditions are right, if you get the gap size and distances right and the screen position, then it would be possible to see an interference pattern on the screen where we have bright and dark fringes. So we call this little, each of these little dark spots here a fringe. Now, from what we know about a similar setup on a ripple tank, we know that this pattern is the kind of pattern we would expect if light is a wave. So what I want to do now is to find the conditions for which we can actually observe these fringes, and by that I mean things like what are the kind of gap size we should use, what are the kind of distances from of the screen from the gaps, and the spacing between the slits, and so on. Simple reason is that if we just simply make two holes on a piece of paper and put a piece of cardboard some distance away and use any light source like a torchlight, we would most likely not be able to see a thing. Well, okay, we will see a bright spot, but we won't be able to see these clear fringe patterns. And I would also like to be able to calculate what are the kind of distances between these bright spots. So for a start, an important condition is that the gaps here, each of the gap here must have a width that is comparable to the wavelength of light. So comparable, we can think of that to mean a few wavelengths, and that's quite narrow. A wavelength of light is kind of a few hundred nanometers, around about 500. Right? There is some range around 500. We'll look at that a bit more later on. Now, so this has to be really narrow slits. Now, the other thing is that the wave, or the light wave coming out from those two gaps must be coherent. So I can't just use just put any lamp next to this, because if I do, the light from different parts of the lamp might not be coherent. Like the top part of the lamp and the bottom part of the lamp, they might not be giving waves in a coherent way. That means when a peak of a wave come out from the top of the lamp, you might not get a peak coming out from the bottom of the lamp, and they may even come out in bursts. So it's all quite random, because a lamp, just because there's nothing to control the different parts of the lamp. So one way to do this is to have another gap before that, is to use a small gap in front of the lamp, and when light from the lamp goes through this small gap, right, only a small part of the light goes through. So around the gap itself, the light could be quite coherent. Okay, quite coherent, and we have the light spreading out along here. Okay, and then when this wavefront spreads out and reaches those two gaps will split the wavefront, this single wavefront, into two new sets of waves. Now in drawing this, let me point out something quite important about light. Now we have all learned since very young that light travels in a straight line. Light travels in a straight line. But remember what I said when I talked about diffraction of waves. When I talked about this diffraction property of waves in a past session, I said that diffraction means that the wave bends around a corner. So the moment I talk about light, I say that light is a wave. That would actually suggest that light can bend around a corner. Now that is something which is very different from what we expect in everyday life. You never think that light can bend around a corner, and you never see it bending around a corner. So it seems like quite opposite to common sense and sounds like complete nonsense. So this is one thing we have to understand. Now, yes, so we would expect light to go straight in everyday life. We would expect light to just go in a straight line. Okay. Now, the reason why we never see with our own eyes, we never see light bending around a corner, is because we never have, well, we almost never, in everyday life at least, get to observe light very closely when it goes through a very, very small spacing, which is just a few times of its wavelength, which is this small, extremely small gap. And even if you have seen light through an extremely small gap, we would never actually have measured it carefully to see whether it bends. So in fact, light, when it goes through a tiny gap, just a few times its wavelength, it will actually bend quite a bit. It can actually bend round quite a bit. Right? And this is the experimental evidence. The very fact that it can produce this fringe pattern is because it has to spread out from these little gaps. Right? It has to spread out. It has to bend round these corners and meet at the screen some distance away. So one of the first thing we have to learn and know when we learn that light is a wave is that light can diffract, light can bend round the corner. But the condition here is that the gap size must be very small. So light cannot just bend around your window, for example. The window is huge compared to 500 nanometers. Okay. So coming back to this, in the experimental setup, we must first use this technique to make sure that light, that light from the two gaps is coherent by using this method of splitting up a single wavefront into two sets of waves. Okay, and we create this single wavefront using yet another small gap in front of the lamp. So it is important. So this setup ensures that the light is coherent. So this is a single wavefront that gets split up. Okay, so these two sources of light split up, spreads out, and those part that bends around would overlap when they reach the screen. And so there was this condition. Let me write this down as well. That the gap size here must just be a few times of the wavelength. So if I gap size here G. The gap must be just a few times of the wavelength, and then the spacing between the two gaps must not be too big either, otherwise they may not actually bend enough to overlap. Okay, so we would expect light to bend, all right, but if the gap size is not that small, they will not bend that much. So it will bend a bit here, and the light will bend a bit there and there, bend a bit here and here. But if the light doesn't bend that much, because it's very hard to make very small gap size, even if you try to cut it on a piece of wood or metal or paper. So for this reason, if the light doesn't bend too much, then the spacing between the two gaps must not be too big. Otherwise, they don't bend enough to actually meet. Okay, so we have to make this spacing quite small as well. And then if they don't bend so much, I'm assuming that we can't make the gap small enough. If the light don't bend so much, then they will only meet that when they are some distance away. So how far away? Some distance which is big compared to this. So maybe if this is a small distance, like maybe a millimeter or so, this distance might say be 1 meter. So I'm just going to put down some numbers and I have to check them later on, but just to get some idea. So let's say this spacing here, I'll call this distance A. Okay, I'll call this distance A, and let's say this distance is maybe about 1 millimeter. And let's say I have a big distance here of maybe 1 meter. I'll call this distance capital D. Okay, and so we can see this condition. As Young might have set it up, we need small gaps for each of the light source. We need a small spacing between the gaps, and we need a big distance. All right, so that if the light, if we can't make the light bend too much, all right, at least we give it enough distance for them to eventually meet at some distance away, and then we can hope to observe some interference pattern, this bright and dark fringes. Let me write down the name which I use for this. Each of these part here is called a fringe. So for example, now that there is, this part is bright, so we call it a bright fringe. Now the next part there is dark, so we'll call that a dark fringe.